So in the given problem, we are given with a cylindrical tube which is cast from solid naphthalene, which is having a diameter of 2.5 centimeters. It is a smooth tube. And now air is enters at one side of the tube with a velocity of 9 meter per second, and the diffusion of the naphthalene into the air is taking place at the atmospheric condition, that is 1 atmospheric pressure, and temperature is of 40 degrees Celsius. Now we need to find out and estimate the tube length required to make the air concentration 25% of its saturation value. As we know, like there is a saturation limit of anything which can dissolve in air. So like there should be a limit of naphthalene which can dissolve in air. So we need to find out the length, or we need to estimate the length of that tube such that the total concentration of naphthalene into the air becomes 25% of the higher or maximum saturation value. And we are also given with some given data at 40 degrees Celsius, that is the diffusivity of naphthalene into the air at this temperature, and the kinematic viscosity is also given of air at 40 degrees Celsius, and we find out the Skimmage number for this temperature and pressure conditions. There are some assumptions that we need to take care of. The first is steady state condition prevails. That means we need to consider that everything happens at a steady state and no change of quantity is there with respect to time. Another is system is isothermal. That means no heat gain and loss or temperature rise or decrease is there in a system. So let's proceed the problem now.
Okay, so in this problem, we are having a naphthalene rod, kind of a naphthalene cylinder. So in this problem, we need to find out that what should be the length of this naphthalene cylinder such that it should diffuse in the air to make the concentration of air 25% of the saturation value. So like the naphthalene rod, it is having some partial pressure, that is P saturation. So according to that, we find out the C saturation, that is saturation concentration according to P saturation. So we need to find out the length of this cylindrical rod so that it should reach the concentration, or the moles should reach the 25% of the saturation value. Okay, so everything is happening at the temperature of 40 degrees Celsius, that is 313 Kelvin, and 1 atmospheric pressure. And the properties, some of the properties are given in the problem. At 40 degrees Celsius, the diffusivity of naphthalene into the air is given 6.61 10 to the power minus 6 meters square per second, and the kinematic viscosity of air is also given 16.95 10 to the power minus 6 meters square per second. And we find out the Skimmage number with the kinematic viscosity by mass transfer diffusivity at 40 degrees Celsius is 2.56. Now we will going to use the engineering correlations and some mass and energy balances to find out our desired length of this naphthalene rod. So starting with the mass balance. Okay, so we know according to mass conservation, when we are applying the mass conservation of the naphthalene, then mass input of naphthalene is equal to mass out or mass output. Okay, so in this case the mass input is due to the convection mass transfer, because air is coming from this side and it is also having some velocity which is also given in the problem, that is 9 meter per second, and the air is obviously at the 40 degrees Celsius. So the mass in is due to basically due to the convection mass transfer, which is the area of the cylinder, that is 2 pi RL or pi dl. So pi dl, and the convection, because this is the case of the convection mass transfer, so we are having the Kc or K mass transfer coefficient, and multiply by delta concentration difference or concentration gradient, that is delta Lm, into the molar mass of the species. If this is mass, then we will have the molar mass of the species. In this case, this is naphthalene, the molar mass of the naphthalene. Now this is the logarithmic, the mean logarithmic concentration gradient of the saturation concentration in air and the concentration of the naphthalene in itself, in the bulk of naphthalene. Now the mass output. Okay, so now the output of the mass output of the naphthalene is due to basically the flow of the air, because air is flowing and the whatever moles are diffused from here to the air, they will going to take out by the air from the another end of the naphthalene rod. So now we will have that is the mass transfer rate, that is equal to density, or moreover we say concentration. So concentration, the bulk concentration of your naphthalene, in the bulk of naphthalene, multiply by volumetric flow rate, that is Q, volumetric flow rate. And now we know that this volumetric flow rate can be written in the terms of velocity and cross sectional area of this cylindrical or naphthalene rod. So this could be velocity, that is characteristic velocity, which is already given in the problem, and multiplying by the area. And we know the area for a cylindrical cross section, it is pi d square by 4 or pi r square. Okay, so this is the second equation, this is the first equation. Now according to law of conservation of mass, these both terms should be equal. So now we're going to equate both of these terms. Now we're going to separate out some terms and we are cancelling them. Now we need this L, the length of that cylindrical rod, and this is Kc, convection mass transfer, that we don't know in this case for these properties, and some properties are already given in the question. Now we're going to expand this term, that is CLM, that is a logarithmic concentration gradient. So now we're going to expand this. So L is equal to C out by Kc delta Lm multiplied by characteristic velocity d by 4. Now here is L. Now we will expand this logarithmic concentration gradient. Now we know that in this case this is CW, that is interface concentration, interface between the air and the naphthalene bulk. So this is the concentration at the interface, and CV out is the concentration of the bulk, and CV in is the concentration in the air. So in this case we are taking the concentration of the air, the naphthalene in the air is 0. So we are assuming the concentration of naphthalene already in air is 0. So we can say CV in is approach to 0 or negligible in this case. So we will neglect the CV in terms from the formula. So now equating the terms. Now we can cancel out some terms, this CV out and CV out, we can cancel them. And now in this case we have a relationship. Now we have some terms and a relationship also, that this is a characteristic velocity, this is Kc, that we need to find out for these conditions. D by 4, this is diameter, we already know. Concentration of the wall or interface, and the concentration of the bulk of the naphthalene. So now we don't know this quantity, so we will use some engineering correlations, because we know that this characteristic velocity divided by Kc is nothing but this is reciprocal of Stanton number of mass transfer. So now we are going to substitute that term in that problem, and also multiply by ln CW CV out. Now the L will be equal to this 1 upon Stanton number and Stanton number of mass transfer, because characteristic velocity upon kc, this is the reciprocal of Stanton number mass transfer, and this is d by 4, and here is the multiply of Cw, that is interface concentration of naphthalene, and Cb out. So like by reducing the terms, we get this final term in terms of like d Stanton number of mass transfer, Cw and Cb out. Okay, for the L, and we need to find out the L. Now we know that this Stanton number of mass transfer, we need to separate out this in terms of other important mass transfer numbers or like engineering correlations. So some of them are for mass transfer, it is Sherwood number divided by Reynolds number and Skimmins number. So this is a correlation. So we can find out the Reynolds number. We already know the Skimmins number, which is already given in the problem, and we can find out the Sherwood number by Linton-Sherwood analogy. Okay, so now we can substitute all of these here. So because this is the reciprocal of Stanton number, so Reynolds number and Skimmins number will be in the numerator, and there is a Sherwood number, diameter by 4 ln, and in this case now we will take out Cw from the denominator in the logarithmic. Cw, this is 1 minus Cb out by Cw, and Cw can be cancelled out. Now it is already given in the question that you should choose the length such that it should make the concentration of air 25% of the total saturation concentration. So that means we are having the Cb out by Cw is equal to 25%, that is 0.25% of the total concentration. This is the total concentration, saturation. So now we have find out one ratio. Now we need Reynolds number and this Skimmins number, this Sherwood number. Skimmins number we have already calculated. We already know the diameter. So now we will find out the Reynolds number for this cylindrical case. So this will be diameter multiplied by characteristic velocity divided by viscosity. So now we can just substitute the values, that is 2.5 10 to the power minus 2. It is already given in the question, diameter in meter, and velocity is 9 meter per second, and this kinematic viscosity is also already given in the problem, 16.95 10 to the power minus 6. Now we are going to calculate these terms and going to substitute here. So we have find out the value of the Reynolds number, that is 13,274 point something. And we know that this term is already greater than 2100, so this is way, like it is in turbulent region, okay, not in the laminar region. So now we will use the equations that are used in the mass transfer for turbulent region, which are Linton-Sherwood. Okay, so we will use Linton-Sherwood here, because the Reynolds number is greater than 2100, and also the Skimmins number is nearly or equal to or greater than 2.56. Okay, so now we will find out the Sherwood number, and it will be according to Linton-Sherwood relation, it is given by 0.023, Reynolds number to the power 0.83, and Skimmins number to the power of 1 by 3. Now we know Reynolds number, we already calculated the Skimmins number, we can easily calculate Sherwood number by the given data.
Go.
So we have calculated the value of Sherwood number by the Reynolds number and Skimmins number using the Linton-Sherwood analogy. So the value is 83.1588. So now we are going to substitute all the values of Reynolds number, Skimmins number, diameter of the pipe, Sherwood number we have already calculated here for this this number of Reynolds number, and we already know this ratio, that is 0.25, already given in the problem. So now we substitute the Reynolds number here. So Reynolds number is 13,274.33. Substituting the Skimmins number, that is 2.56, and the Sherwood number And now we are having the diameter that is already given in the question, 2.5 10 to the power minus 2 by 4 ln. This numerator is 1 and this is 1 minus 0.25. Now we are going to calculate this value, and we can easily calculate the length of the required length of this tube that we needed to make the concentration 25% of the total saturation of the naphthalene into the air. Okay, so with the help of the given data, we have find out the value of length, that is 0.7374 meters, or we can write in terms of centimeter, that is 73.47 centimeter. So this is basically the required length according to Linton-Sherwood analogy. So the required length is 73.74. Now for the same Reynolds number that is in the turbulent region, we are going to apply the Gilliland-Sherwood analogy to find out this same length for the another approach. So now applying the another approach of Gilliland-Sherwood analogy, we will apply the formula for the Sherwood number. Now we are already given with the Reynolds number and the Sumit number that we already calculated, same as the Linton-Sherwood part, that is 13,274, and the Sumit number that we already calculated, that is 2.56. Now we just substitute the values and we can get the answer. And writing the Sumit number. And now we can calculate the value of Sherwood number. Okay, so we have calculated the value of the Sherwood number by the relation of Gilliland and Gilliland-Sherwood correlation with the help of Reynolds number that we have already calculated and the Sherwood number that we have already calculated in the previous problem. Okay, so now we're going to find out the length of that tube, the cylindrical tube, by substituting the values in this relation, that the general formula that we are having for the length and the Sherwood number, Sumit number, and all the quantities. Now substituting the same values and the same type that we already did in the first part of the Linton-Sherwood correlation. So now L is equal to, writing the Reynolds number 13,274.33 and the Sumit number, now the Sherwood number, and now this diameter, that is 2.4 in the meter we are writing, so divided by 4, and this will be remain same. Only the Sherwood number will going to change in this problem because we have only changes the Sherwood number relation. First we are using the Linton-Sherwood, now we are using Gilliland and Sherwood correlation. Now we are having, now we are going to just calculate the value of the length in meters, okay, for the Gilliland-Sherwood relations. Now we are just we can just calculate this value by putting in the calculator. Now by putting these values in the calci, we find out the value in the meters, that is 0.6647. Now we can also write in terms of centimeter, that is 66.47. So now we have calculated the value of length of that naphthalene tube that we require for this much of concentration, this much percentage of concentration of naphthalene in the air. So by the help of that Linton-Sherwood relation, we have find out that is length, that is 73.47, and from Gilliland and Sherwood correlation we have find out the length as 66.47, that is nearly close. Okay, so this is all about the problem on the mass transfer, or diffusion of naphthalene into the air.